In this clip, I want to give a sort of high-level overview of this module, not from a sort of what we're going to cover perspective, so much as how the things relate to each other. So really, this module is about the question of how do we model dynamics of particles. So dynamics means how do we figure out what the position of the particle as a function of time is and what the velocity of the particle as a function of time is, right? We want to know how the particle's state variables evolve in time. And particles refers to the idea that in this module we're not interested in sort of extended bodies and how they rotate. We're instead interested in basically taking extended bodies and compressing them down from an abstraction perspective to point masses, and then asking questions about how those point masses move around. Okay? So that's the overall question that we're dealing with in this module. Let me outline what the general sort of process is that we're going to exploit in doing that, and it's the process that you are pretty familiar with already from ModSim, I expect. The first thing that we need to do is we need to identify the sort of chunks and the interactions. Okay? So what we're basically doing is asking the question, how am I going to think about this system? How am I going to abstract it? Am I going to think about this as one point mass or as multiple point masses? Am I going to take gravity into account, or am I going to take drag into account? What are the different kinds of forces I'm going to take into account? Okay, and so when I identify chunks and interactions, the sort of output of identifying chunks and interactions is that I have one or more free body diagrams. So maybe let's say I'm, for example, interested in modeling this situation where I've got a ramp and I've got a block, and the block is free to move and the ramp is free to move. I might abstract that and say, actually, you know what, there's not going to be any rotation in this situation until the block hits the bottom of the ramp. So it's appropriate to use a particle abstraction. And I might be interested in how this block moves and how this ramp moves, so I'd like to know the dynamics of both the ramp and the block. So to that extent, I'm going to identify two chunks. One chunk is the block, right? And I say, okay, that's a chunk. I'm going to cut that out. Free body diagram, draw a free body diagram of that. So I've got gravity acting on that. I've got a normal force acting on that. Maybe there's a frictional force acting on that. I also am going to cut that ramp out of the rest of the universe. So there's a normal force from the block that's acting on the ramp, another gravitational force that's acting on the gravitational force acting on the ramp, a normal force from the ground. So this is normal force of the ground, normal force of the ramp, and then obviously there would be some frictional force here. Maybe there'd be some frictional force on the ground, right? So what I've done in drawing these two free body diagrams is I've said I'm thinking about this system as consisting of two point mass chunks. One point mass chunk is this block, one point mass chunk is this ramp, and I'm thinking about this system as having a number of interactions present. There is friction present, there's a normal force present, there's a gravitational force present. I've abstracted away the idea that there might be drag present. I've abstracted away the idea that maybe this block could rotate. I've abstracted away any other forces that might be present. So I've identified my chunks and I've identified my interactions. Okay? You'll note that I haven't talked at all about a coordinate system yet. I haven't talked at all about equations of motion yet. I've just said this is how I'm thinking about the system, what the chunks are, and what the interactions are. The second thing that I'm going to do is identify a coordinate system. And in this particular case, I probably would identify something that looked like this. I'd say, okay, well, I'm interested in knowing what the location of the front of the block is, so maybe I'll define this distance as being d, and this vector as being d vector going, so this is my origin, so d vector goes from the origin to the tip, and then maybe r vector goes from the tip up to the center of the block. So I could actually talk, if I talk about the block as being B and the ramp as being R, then the position of the block is d vector plus r vector, and the position of the ramp is simply d vector, right? So I've defined a coordinate system, I've defined sort of effectively some unit vectors, right? There's an r hat vector, there's a d unit vector, there's a z hat unit vector. So I've got my coordinate system defined at this point. Okay. The third thing that I will end up doing once I've defined the coordinate system is I will figure out what my equations of motion are. And that has a couple of sort of sub-steps in that. One is that I can write down the sort of high-level equations of motion very easily, because those simply tell me that the sum of forces on the block is equal to the mass of the block times the acceleration of the block, and the sum of forces on the ramp is equal to the mass of the ramp, which I think I'm calling big M. Let's just call it m sub r and m sub b, right, times the position of the ramp, the second derivative, or the acceleration of the ramp, right? So that's the sort of simple equations of motion, but at this point now I need to actually blow these out a little bit and both blow out the right-hand side, so I need to make these more explicit in terms of what the coordinates are for the system, and I also need to make these more explicit. I need to figure out what are the mathematical models for the different forces. So in blowing out the left-hand side, I need to figure out mathematical models for the forces, and blowing out the right-hand side, I need to basically be more explicit about my coordinate system and deal with derivatives of my coordinate system. So for example, if I think about what the blowing out this right-hand side are, right-hand side is, if I think about, say, the block, right, well, the sum of forces on the block is a frictional force, so frictional force on the block, plus whatever the normal force is that the ramp applies to the block, plus whatever the gravitational force is. Well, the gravitational force is pretty easy to write, so let's say that's minus mg j hat, right? So we got I hat defined, got j hat defined, and we also have r hat defined. Note that what I called d hat before is the same as I hat in this case. My frictional force is going to be some frictional force, but it's always going to be in the r hat direction, right? It's always going to be along the surface of the ramp. My normal force will always be along a direction that is normal to the ramp, and I'm going to call that n hat. So let's draw the ramp here. So this is n hat, this is r hat, right? And my gravitational force is always in the j hat direction. If the block is moving, I could go one step further and say, okay, my frictional force here is u sub k times n sub r times r hat, and I need to think about what the sign of that would be. It would actually depend on what direction the block was moving. My normal force remains a constraint force. I don't know what it is yet. And of course gravity is pretty well defined. Right? So that's about as far as I can get as far as expanding mathematical models for the forces for the block. And then on the right hand side, obviously I've got something that I can write in terms of I hat and j hat, or something I can write in terms of r hat and I hat. So let's do that. So let's expand the right hand side. So if I'm expanding the right hand side, the position of the block is, I'll say, d of t times I hat plus r of t times r hat, where d is this distance from the origin. It's how far do I have to go to get to here, and then r is the distance from the tip of the block up to wherever the block is located. Right? The derivative of the block's position is simply d dot times I hat, because I hat doesn't change in time, plus r dot times r hat. I will note there's an r hat here. It is not an r hat that is changing in time because the angle of this block is not changing in time. So the derivative of r of t times r hat is simply r dot times r hat in this particular case. And finally, r sub b double dot is d double dot I hat plus r double dot